All right, so this video for the review is only going to cover the first page. I'm going to kind of break this one up so it's not one super long video. We'll just kind of go a page at a time. So this front page, for the most part, you're just evaluating integrals. Number one, it wants you to evaluate the integral of pi x plus 8 dx. So we know that our x goes up a power, which means we also have to times by the reciprocal 1/2, but we already have that constant pi in front as well. And then the 8, because it doesn't have an x, it gets an x. We don't have to worry about multiplying by anything because it's just an x to the power 1. And then we have a plus c. So number 1 simplifies to pi halves x squared plus 8x plus c. Be really careful not to forget that c on these integrals. When you're doing definite integrals where there's bounds, we don't worry about the plus c, and we've been doing that a lot lately. Don't let that affect you on these ones. You've got to have the plus c when we don't have a limit of our integration. So number 2, 2x to the 4th plus 3x squared minus 2x. The x to the 4th becomes x to the 5th, and I have to multiply a 1/5 out in front, the reciprocal, and I already have a 2 in front of that one. 3x squared, the x goes up to 3. I have to multiply by a 1/3, and I already have a 3 out in front. And then the 2x becomes 2x squared, but I have to multiply by 1/2, and then, of course, my plus c. So I end up with, what, 2/5 x to the 5th, plus my 3's are going to cancel each other out, so I'm just going to end up with an x cubed. And then my 2 and my half are also going to cancel, so I get a minus x squared plus my c that I'm not going to forget. Number 3, I probably want to rewrite that 7th root of x cubed. I'm probably going to rewrite this one to make it a little bit easier as 2 plus, that's going to be x raised to the 3/7 power. Remember, whatever's in front of that root becomes the denominator of your exponent. So when I integrate, dx. When I integrate, my 2 goes up to a 2x. My x to the 3/7 becomes x to the 10/7 because I'm going to add 1, but then I have to multiply by the reciprocal of that, which is 7/10. And it's not going to clean up from there, so I just need to remember my plus c, and I'm good. Number 4, you might be tempted to do u substitution right now, but if I were you, I would start by trying to simplify what I can first. And we had this trick that we used. We took that root on the bottom, and I'm going to rewrite this as 4 plus 5x raised to the 3/2 over x raised to the 1/2. Because I want to move that x to the 1/2 to the top, and I'm going to rewrite this again as 4 plus 5x to the 3/2, but I'm going to now be multiplying that by x to the -1/2. And we're going to actually take that x to the -1/2 and distribute it to everything on the inside. So I end up with the integral of 4x to the -1/2. And now 5x to the 3/2 multiplied by x to the -1/2. Remember, you take the -1/2 and the 3/2, and you are going to add those together, which gives you 1. So you just end up with plus 5x, and then I have my dx. This is a lot cleaner than trying to use u substitution or any other method, because now I just have 2 separate integrals. Well, I can treat it as 2 separate integrals, right? So I just have to integrate the first part and the second part. So my answer is going to become the x to the -1/2 goes up to x to the +1/2, and I already had a 4 in front, but because I went up to a power of 1/2, I have to multiply by the reciprocal 2/1. And then my 5x is going to become 5x squared, but because it's a square, I have to multiply by 1/2, the reciprocal, and then I've got my plus c. So when I clean this up, 2/1 times 4, that's just 8 square roots of x. And then 1/2 times 5, we're just going to write that as 5/2 x squared plus c. If this was a free response question, you could stop at this point right here. You wouldn't have to simplify that any further. If it was multiple choice, they would probably combine things and make it look a little bit cleaner than that. So you really need to know how to do both, but just know on the free response that last step would not necessarily have to happen. Okay, number 5, evaluate the integral. Again, you might be thinking use substitution, but let's try to use some trig identities to simplify this one first. The one I'm going to use, and one of the ones, there's two that we use the most, right? We use the sine squared of theta plus the cosine squared of theta is equal to 1. The other one that we use a lot says that 1 plus the tangent squared of theta equals, do you guys remember this one? The secant squared of theta. So if I look at the bottom, I see this on the bottom, and I want to replace it with secant squared. So I'm going to rewrite this integral as secant cubed tangent theta over secant squared of theta d theta. Now my secants on the bottom are going to cancel with 2 of my secants on top. So I end up with the integral of secant theta tangent theta. Going backwards, again, now that I'm going to take my integral, I want to go backwards, and using my derivatives of trigs, remember that the derivative of secant is secant tangent. So when I'm going backwards, that means that secant tangent just turns into secant of theta, but I also have a plus c. I don't want to forget about that plus c. So that right there would be my final answer after I take my integral. Number 6, find y equals f of x if f double prime of x is x plus 2, f prime of 0. Okay, so it gives me f double prime, and it wants me to work backwards until I get back to my original f of x function, which I can do because it gives me these initial conditions. The problem doing this without those initial conditions is I've got my c value, right? Every time I take an integral, I have this plus c. If I don't know anything about my initial conditions, I can't replace that c with an actual value. But because it gives me initial conditions, I'm going to be able to replace my c. So I'm going to start by taking the integral of f double prime, which is just the integral of x plus 2. When I do that, my x goes up to x squared, but I have to multiply by 1/2, and my 2 becomes 2x, and then I have to remember my c. All right? Now remember, when I take the integral of f double prime, that takes me backwards to f prime. So my integral becomes my f prime. And I would be stuck without that initial condition. But since I know this one right here, f prime of 0 equals 3, what that means is when I plug 0 into these x values, my f prime value is going to become 3. So I know that 3 is equal to 1/2 0 squared plus 2 times 0 plus c, which is nice because that cancels, and that means that 3 is equal to c. So I can go back, and this c value right here, I can replace, and I'm going to write that in red so that we know we replaced it. That c value is going to become 3. All right? Now that I know what c is, I can take my integral again. So I'm going to take the integral of f prime of x, because that's going to give me f of x. So I'm integrating 1/2 x squared plus 2x plus 3. And when I do that, when I take the integral of f prime of x, I'm going to end up with f of x. And the integral, so let's do one piece at a time. X squared becomes x cubed, but I have to multiply by 1/3. I already have a 1/2, so that 1/2 and 1/3 are going to become 1/6. And I know that's kind of skipping a step, but I'm lazy and I don't feel like writing that more than once. So I have 1/6 x cubed, and then the integral of 2x is going to become x squared, but I have to multiply by 1/2, which conveniently cancels out my 2 that's supposed to be in front. So that 2 times 1/2 goes away, and I just end up with x squared. And the integral of 3 is just 3x, and then I have plus c. Now this c value is different than my old c value. Please don't replace this with a 3. This c is just some constant. I don't know what it is yet, but it's a new constant, and I'm going to use my second initial condition. I know that when x is 0, f of x is -1. So I'm going to go and I'm going to plug that into my f of x function. And I'm running out of room here a little bit. So we're going to say -1 is equal to 1/6 0 cubed plus 0 squared plus 3 times 0 plus c. So everything cancels except for the c, which again, that's nice and convenient that c is equal to -1. That's not always going to happen. The initial condition isn't always going to be x equals 0, but it sure is nice when that does happen, because now I know that I can plug this in where that c value is. So I'm going to replace that with in fact, I'm going to replace the entire +1 with plus c. I'm going to replace that with -1. So this becomes my y equals f of x. That's my original function. If I wanted to double check, I could take the derivative and then take the derivative again, and I should end up at x plus 2. Okay, number 7, an object has a constant acceleration of 42 feet per second squared, an initial velocity of -18 feet per second, and an initial position of 3 feet. Find the position function describing the motion of this object. Okay, so this is a little bit different because it's giving us all the pieces of our straight line motion. It's giving us the pieces and it wants us to write it as a function. So usually position we write as s of t, right? That's usually what we use when we're talking about the position of something. And it tells me that my constant acceleration is 42 feet per second. And if you think back to the functions that we've used in the past, it usually looks something like this. It usually starts out s of t equals -1/2, and then there is some t squared function, and that's our acceleration function, right? So there's usually something, and I'm going to put a t squared, and that a is not necessarily a specific value. It could be. In this case, it's 42 feet per second squared, so I get a t squared, right? But it's usually our acceleration. When we're dealing with gravity, that's our, -9.8 if we're dealing with meters, and -32 if we're dealing with feet, which doesn't really matter in this question. It might come up later on. But we don't know, we're not dealing with gravity, we're dealing with this constant acceleration. And then we usually have our v naught t term, which is our initial velocity multiplied by time. And then we end with our initial position, our s naught. So when I take the pieces this problem gave me and I try to fit them into the formulas that we've seen in the past, I'm going to get -1/2. My acceleration is 42 feet per second squared, so 42 t squared is going to be my acceleration. Actually, you know what? We don't know if we're going up or down, so we probably better just use +1/2. So 1/2, 42 t squared, and then I'm going to add my initial velocity, which was -18. So maybe we'll just get rid of the plus and do -18 t. And then I end with my initial position, which was a +3. So that would be the function that I would use. And in chapter 5, we're going to spend an entire homework doing more straight line motion. We're going to look at distances traveled, which kind of relate a little bit more to 8 and 9 that are coming up. Number 8 gives us an acceleration function, and it wants us to, find the position function. So it's going to start us with acceleration, and it wants us to work backwards to get our position. And if you remember, if we start with position and take the derivative, we get velocity. And if I take the derivative of velocity, I get acceleration. So what it wants me to do is it's starting me with acceleration, and it wants me to go backwards and find the velocity function. And then it wants me to go backwards from there and find my original position function. And because, just like the problem earlier that gave us initial conditions, it gives us a velocity at a certain time, and it gives us a position at a certain time. So we are going to be able to work backwards to get our initial position function. So I'm going to start by taking the integral of my acceleration. So that means I'm taking the integral, where did my pen go? I'm taking the integral of 12t minus 6 dt. And this is going to equal my velocity function. So my velocity function is equal to, I've got to square the t. It's t squared, which means I have to multiply by a half. So it's going to take that 12 and it's going to turn it into a 6. And then my minus 6 is going to become minus 6t. And then I have a plus c that I need to fix, right? So now let's use our initial conditions to find out what that c value is. It tells me that my velocity is 20 when my time is 2. So my velocity is 20 when I plug 2 in for my time. So minus 6 times 2, and I still don't know what c is. That's what I'm trying to figure out. So I get 20 is equal to 6 times 4, which is 24, minus 12 plus c. So 24 minus 12 is going to give me 12. And then I am going to minus that from my 20. So c is going to equal 8. That looks right. So instead of c back here, and I'm going to mark this in red. If c is equal to 8, I'm going to plug that in right there. So my plus c becomes plus 8. So now in order to find my position, I need to take the integral of my velocity. So I'm going to take the integral of 6t squared minus 6t plus 8. And I'm going to work backwards, and when I do, that's going to give me my position function. So the integral of 6t squared, the t goes up to become 3, but that means I have to multiply by a third. So 6 times 1/3 becomes 2. My minus 6t becomes t squared, so I have to multiply by a half, which changes my 6 into a 3. And then my 8 just goes from 8 to 8t. And then I, of course, have a new c value. It's not 8. It's not the same as my other c value. I've got a new one that I've got to deal with. So I'm going to use my second initial condition. And I'm going to plug that in so that I can find out what my new c value is. So I'm going to work down below a little bit. I know it's in the space of another problem, but I'm running out of room. So I know my position is 5 when t equals 1. So when t times 1 cubed minus 3 times 1 squared plus 8 times 1 plus c. So 5 equals 2 minus 3 plus 8 plus c. So 5 equals what? Negative 1 plus 8 is 7 plus c. So c is going to equal negative 2. And I'll let you follow that step by step later if you need to. But I'm just getting c alone. I'm moving everything to the other side. So c is equal to negative 2. So I can take that c value and I can plug it in back here for my c value. So I'm going to put a minus 2 right there. So my position function, S of t, is 2t cubed minus 3t squared plus 8t minus 2. That would be my final answer. Okay, number 9. Of everything on this front page, this is probably the one that you're going to have the question on, because when we eliminated some of the worksheet questions and replaced it with Delta Math, this is one of the questions that we didn't see anymore. And I didn't realize that until we were starting to do this review. So a point moves in a straight line so that its distance, its position, at time t from a fixed point of the line is 4t minus 2t squared. So my position is 4t minus 2t squared. What is the total distance covered by the point between t equals 1 and t equals 3? So it wants me to find the total distance that I travel when I go from 1 to 3 in time. From 1 second to 3 seconds, or 1 minute to 3 minutes, or 1 hour to 3 hours, whatever t is, whatever units, I want to know what happens from 1 to 3, how much distance I cover. Now there's a key word in here, that total distance, because one of the things that we have used a little bit is to find the distance something travels, we use the integral. And again, this is something we haven't practiced as much, and I hope that this example gives you an idea, some framework to kind of work off of. So there's two different distances that we can find using integrals, okay? If I take the integral from 1 to 3 of a velocity function, if I take the integral from 1 to 3 of my velocity, that is going to give me my displacement. That is going to tell me how far away I am from where I started, okay? Going from 1 to 3 of my velocity function tells me my displacement. How far am I from where I started? Going from 1 to 3 of the absolute value of my velocity function gives me my total distance I traveled, okay? So I can't just take the integral of my velocity. I have to take the integral of the absolute value of my velocity. Because basically what happens if I'm looking at my velocity function, if I'm moving to the right, I'm up here. If I'm moving to the left, my velocity function's at the bottom. But I'm still moving. So if I just take into account my velocity function and I go from, let's say this is 1 and let's say this is 3, if I don't use the absolute value, it's going to count this as moving to the right, and it's going to count the underneath area as moving to the left. So those are going to cancel each other out. They're going to outweigh each other, and it's going to tell me where I ended up compared to where I started. If I take the absolute value of my velocity function, the difference that's going to make is instead of this part right here being under the curve, it's going to bump that up above the curve. So when I take my integral, it's now considering the fact that I'm still moving. It doesn't care that I'm moving in the negative direction. It's just taking my negative movement and counting that as movement. All right, I know that's a lot to take in a 90-second explanation, but you need to know when you're trying to find total distance, we are taking the integral of velocity of the absolute value of velocity. So this is the one that we're going to use right here. We're going to use that total distance function. This is the one that we want. So in order to take the integral of velocity, well, first of all, I need to find my velocity. Right now, all I have is my position function. So I need to find s prime of t, because that's going to equal my velocity function, right? So 4t becomes 4. Negative 2t squared becomes negative 4t. So my velocity function is 4 minus 4t. So now in order to find my distance, I'm going to take the integral of that function, and I'm going to go from 1 to 3 of 4 minus 4t dt. But I need to do the absolute value of 4 minus 4t. Absolute value integrals. The good news about them is they are going to come in two forms. One of them, they're going to be straight lines. Okay, 4 minus 4t, that's just a straight line. That's not too hard to do the absolute value of a straight line. You just find out where the vertex is. For example, this one, if I were to draw this picture, I'm going from 1 to 3. If I were to graph this as an absolute value, the first thing I'm interested in is where is my vertex. So I set the inside equal to 0. So that means that 4t equals 4, which means that t equals 1. So at t equals 1, I have a value of 0. Now looking at this, I can derive a couple of things. 4 minus 4t means I have a slope of negative 4. So my original function is going down 4 and over 1. So by the time I get to 3, I'm down here at negative 8. Okay, this point right here is 3 comma negative 8. And going the other direction, I'm going to go left 1, I'm going to go up 4. So this point is 0 comma 4. But I'm not interested in 4 minus 4t. I'm interested in the absolute value of 4 minus 4t. This part's okay. It's already positive. It's above the x-axis. But the rest of my function, I need to mirror. I need it to go up and do the same thing it's doing when it goes down, but I need it to do it above the axis. So drawing this picture isn't too hard. Instead of going down 4 and over 1, I'm just going to go up 4 and over 1. So at this point 2, I'm up 4. At 3, I'm up 8. That's not a hard picture to draw. Algebraically, it's not that bad either. I would have to split up this integral because when I go from 0 to 1, I'm using my 4 minus 4t function, right? Because my line right here is going down. But when I go from 1 to 3, I'm not using 4 minus 4t. This line right here is not 4 minus 4t. It's 4t minus 4. It has a positive slope of 4, and it's going to cross down here at negative 4. I know my picture's not to scale. Sorry about that. That's what the absolute value looks like. The way you solve this, there's two ways. Again, the nice thing is usually they're straight lines. And with a straight line graph, all I have to do is find the area from 1 to 3. Remember, the integral from 1 to 3 is just the area under the curve from 1 to 3. So if I find that area, that's just a triangle, right? So my area is going to be 1/2. My base is 2 wide, and my height is 8. So I get 1/2 times 2 times 8. So that means my area is going to equal 4. No, it's not, because I'm canceling out my half. My area is going to equal 8. So my total distance traveled is 8. In fact, I'm going to the left. This entire time when I'm going from 1 to 3, my original function, I'm actually moving to the left, but I'm moving to the left 8 units, whatever that amount of unit is. All right? I think doing this graphically is a lot easier than doing this algebraically. If you were to do it algebraically, you would be going from 1 to 3 of the absolute value of 4 minus 4t dt. Well, the absolute value of 4 minus 4t from 1 to 3 is actually 4t minus 4 dt. So if I were to evaluate that, the integral of 4t is t squared divided by a half, so 2t squared minus 4t, and I would be evaluating that from 1 to 3. So when I plug in my 3, I get what? 3 squared is 9. I get 18 minus 12, which is 6. But then I have to subtract plugging in the 1. So when I plug in a 1, I get 2 times 1, which is 2, minus 4 times 1, which is negative 2. So I would be doing 6 minus negative 2, which gives me 8. So algebraically, I get the same answer I get when I draw the graph. If it is giving you a more complicated picture, you're not going to have to do it by hand. It's going to be a calculator question. So absolute value questions are good because they're either easy straight lines that you can do graphically using the picture, or they're complicated absolute values and you just use your calculator and it does the work for you.